All right, awesome. We're here. How's everyone doing? Super, super good. Excellent. Lectures. I feel like you swam a mile. Oh, man. Okay. Yeah, I get my shot Monday, so we'll see how that goes. I get it at like 7 in the morning, so I should have time to recover, hopefully. Yeah, was that first? I'm getting my first. Was that your second? First, okay, interesting. Yeah, I'm hearing from people that the second one sometimes really knocks you. But, you know, we'll see. Alrighty, so, took your second on Wednesday. Oh, cool. Awesome. Yeah, that's sort of what I'm hearing from people. I've heard from people it's kind of like having the flu, except you don't have the flu. But people are saying sometimes it feels just like that. All right, so I downloaded your 223 repositories this morning at 8 and started grading those, but I'll hopefully get through those probably tomorrow, but if not tomorrow, Sunday. Incidentally, if you don't want me to grade your PA1 as it stands right now, in other words, if you're choosing to turn it in up to 24 hours late and you don't want me to grade it the way it is right now, send me a note, okay? Because if you're pushing, if assuming you pushed it over to GitLab already, send me a note and say, hey, hold off on grading this until Saturday. Otherwise, if your repo is available, I'm going to grade it the way it looked this morning at 8 o'clock, which I believe is probably what most people intend. But, you know, if you really wanted that extra 24 hours, let me know through an email. Otherwise, I'll just grade it as is. All right. Any lingering, burning questions on PA1 before we move on? And we'll obviously talk about PA1 in detail on Monday after I've graded them. All right, cool. Let's go on to PA2. Let me put this on a different window. All right, so PA2 is a revisiting of our favorite assignment, which is building a word index on a file. So basic setup, you're going to write a program that you can feed a text file, and it will go through and it'll look at each of the words in there, and it will record an index of where those words occur, right? Position being just word count from the beginning. So when you're done, you get a list of words that are in your file and the position at which they occur. And so this is like something we did in 224. We used awk instead and stuff like that. But we also used an associative array, and we're going to do the same thing here. We're going to use a hash map, which is, you know, a hash table and associative array. So this is, you know, a 7-page write-up on the assignment, and we'll talk a lot about it. And the assignment is fairly complex in the sense that there's a lot of parts and pieces to it, and we're going to end up with some really, really high-powered classes and using some classes in some really high-powered ways. But the amount of code you have to write for this is probably pretty small. Okay, so I put together a solution for this. It was 84 lines, and about half of those didn't do anything. They were either white space, or they were just an opening or closing curly bracket, or a comment with nothing else on it, and so on. So 40-some lines of Java is enough to make this project. Okay, doesn't mean you have to do it in 40 lines, But if you are shifting over to the mindset of working with objects and really thinking about objects and what it means to be an object, you can start doing some really powerful things in 1 or 2 lines of Java. Okay, and that's part of the goal of this exercise, is to, continue that shift into that mindset where, in C we've got variables. And if you want to do something, you pass your variables to a function, right? In Java, we have objects, and there's methods that are actually a part of the object. And so, for example, if I have a linked list of strings, and I want to know what the length of the last element in that linked list is, right? What can we do in Java? We could say, list.get, which will get the last element of my linked list. And if that's a string, I can say .length, and that will give me the length of that string. Or I could say character at 0, which would get me the first character of the last string in my list. And I could say to uppercase, which would convert to uppercase the first character of the last string in my list called list. Right? And we can start putting these things together. And in C, we would probably say, node equals, get last node. And then we'd say, data equals node arrow data. And then we'd say, character equals data bracket 0, and then we'd say, uppercase equals 2 upper parentheses, etc., right? But if we think of this as being a character, right? This is a linked list. This is a method which returns a string. So this is a string, and strings have a character at method. And so if we say string character at and we pass 0, this whole thing is the first character, which is a character. And characters have a method called toUppercase. And so this is using the toUppercase and the character method of the character, which is at position 0, in the string, which was gotten by the get method in the linked list. Alright, so all that alphabet soup is basically saying we want to move towards this kind of thinking. So keeping that in mind, let's take a look at PA2. And this is all kind of speaking to that, right? Which is the idea that you can't do this in one day. Unless you're already, a Java programmer, or you're already, versed in object-oriented programming, you're not going to be able to do this in 1 or 2 days. Okay, you have a week to do this. It's due a week from today. But it's going to take, a few of those days to get deeper and deeper into this mindset. And it's going to involve thinking about how you're going to put this together and designing it before you start writing code. And then writing some code and maybe stopping and redesigning it and going back and rewriting your code and maybe doing that 2 or 3 times. Okay? This is time well spent, because this will make it possible to do the subsequent programming assignments and the stuff that you're going to meet at a university. So start early, ask lots of questions, right? Stay away from IDEs, don't use Eclipse, IntelliJ, etc., etc. Work from the command line. That'll help you with the syntax. It'll help you keep straight what it is that you're doing at each point. All right? So your goal is to make a single class. The class is called Indexer. Okay, just like you did a fraction class for PA1, you're making a class called Indexer. And Indexer basically lets you open a text file, pull in the contents, look at words, build an index of them, and then ask questions about that index. All right. The class has a single constructor which doesn't take any arguments and doesn't do anything in particular except whatever you need it to do, whatever initialization you have to do internally, and so on. Doesn't print anything, doesn't take arguments, doesn't return anything, right? It's your init method. So you need to provide a number of methods. The first one is process file. Okay, so if I have an index called ind and I've constructed that, I should be able to say ind.processFile, and give it a file name. And this does all the magic, right? When I do this, the result is that inside this object, IND, I now have a fully built data structure which has all the index information about this file. So this is the only place where you touch the file. And what you're going to basically do is open the file, read it in word by word, and as you get each word, update your internal index, your data structure. And when you're done, close the file. You're done with the file. Now you've got this structure that has all of your index information. So this is the indexer. Alright, once you have an index, you can explore it by using any of these methods. So number of instances takes a word and returns an integer. And it tells you how many times that word appears in your index. So if the word is hello and the word hello appears 5 times, number of instances, parentheses, quote, hello should return 5. If the word doesn't appear anywhere, return 0. That's how many times it appears. But most of these, if you try to run this method and you haven't yet built an index, that's an error. Return -1. Don't print anything, just return -1. Right? You can fail to have an index because you never called process file, or you called process file on a file that you couldn't open. It didn't exist, you didn't have permission for it, something. So if anything goes wrong, or if you've never called this, you need to know that. So that you can say, hey, I don't have an index, I can't tell you the number of times a word occurs in this index because I don't have an index. Return a -1. Okay, location of will tell you where in the original file a particular word was located. And because words can occur more than once, you also tell it which instance of the word you're asking about. So if I say location of hello, comma 0, I'm asking where's the first occurrence of the word hello. Okay, again, 0 means first occurrence, 1 means second occurrence. Usual business there. So location of hello, comma 0, tell me where the first occurrence of hello is. That should be an integer that gets returned. If I say location of hello, comma 3, that should tell me where the fourth occurrence of hello was in my file. Return that as an integer. Alright, if you haven't processed the file yet, return a -1, that's an error. If the word is not anywhere in the file, return an error, -1. If you ask for something silly like hello only occurs 5 times, and I ask for the 75th instance of hello, that's an error, return -1. If I ask for the -7th occurrence of hello, that doesn't make any sense, return a -1. Right, so these are just different edge cases to error out on. But in general, right, find the nth occurrence of the word, return the position of that. And the number of words tells me how many unique words there are in the index. Again, -1 if you haven't built an index yet. And then toString should print out a really nice looking complete dump of your index. Word followed by the number of the locations where it appears in the file. Next word followed by the locations, and so on and so forth. Alright, that's the interface to the outside world. These are the methods I'm going to call and play with from my main program. And most of these are 1 or 2 lines of Java if you've got things set up right. Right? Number of words, that's a 1-line method. toString, that's a 1-line method. Location of, that can be a 1-line method. Number of instances, 1-liner. This is the one that's going to do most of the work. Process file, that actually builds the index. Okay, and that and a few of these other things are built on a set of private methods that I need you to implement also. These are required. The first is called cleanupWord. So your words should all be uppercase. They should not include any punctuations, numbers, anything that's not a letter. So if you have the word DON''T, that should be converted to uppercase DONT. If you have hello, hello exclamation mark, hello comma, hello with uppercase or lowercase, or hello with a number in the middle of it, those are all uppercase HELLO. They're all the same word. So before you start taking your words and building your index from them, the very first thing you're going to do is clean them up. and I want you to make a method called cleanupWord. Takes in a word and returns a cleaned up word. And you do that by basically using character.isLetter to see if it's a character that you want. Use character.toUpperCase to convert it to uppercase. And build a clean string from the input string. Alright, we're going to add more detail to all of this as we go. The other private method I'm listing here is add reference, and this is the real workhorse. Okay, add reference and cleanup string together give you process file. So what does add reference do? It takes a word, it takes an integer location, and it adds that information to your index. Okay, how do you do that? So you're going to implement this whole index as a hash map, an associative array. The key is going to be the words. The value associated with the key is going to be a linked list of integers, which contains the locations where that word appears. So to add a word to our index at a particular location, you do two things. First, you look in your hash and see if the word is there already. If it's not, you have to add it. So add it to the hash, put in an empty linked list. And then you take the linked list associated with the word and you just add that location to the end of it. Alright, and again, if you try to do this and the index has not been, no file has been processed, you don't have a file open, it's just an error, don't do anything. Alright, and you're going to want one private field at least in your class called index, which will store the actual index that you're building, and that's going to be a hash map. Okay, we're going to talk about hash maps in a little bit. We're going to go through scanners. Again, we're going to go through files and so on. So here's how you can do this. Okay, so you can take this and you can go off and you can start writing code, and you're probably going to get to a few hundred lines really quickly, and it's going to get more and more muddled, right? And that's okay. If you want to do that, that's totally fine. That's a really good way to learn this stuff, to get better at it. But if you don't want to do that, right, here's how you can implement this. Alright, now I'm going to give you some suggestions at the end also that are optional, but for how to approach this in pieces. Okay, so here's the implementation I'm thinking of. To process a file, open it using a scanner. We played with scanners yesterday or Wednesday on standard in, so we'll look at how to do that on files. So open the file with a scanner. Start a hash map, okay, named index, and the keys that we use to associate with data are strings. Those correspond to words. The values are linked lists. That's an array, basically an array of integers. Alright, you're going to need to keep track of what word you're looking at in the file, so just make a position counter variable. It's just a plain int, and every time that you get another word to add, bump up that index. Okay, so initialize your position counter to 0. And read a next word from the scanner. So we're going to use has next and next. Has next will tell us if we have another word, and next will give us the next word. This is like has next line and next line that we did Wednesday. But these are for tokens, and default token is, you know, non-space separated by space. So basically a word. So get a word using next, and then clean it up using cleanupWord. Alright, you need to check at this point to see if the word is empty. Because if you ingested a word from the file, like, you know, 123, that's not a word. When you turn it into something that just has uppercase letters, it's going to be an empty string. You don't want to add an empty string to your hash. So check to make sure it's not empty. Assuming it's not empty, increment your position counter because you have a new word, and then just call add reference. First argument will be the word, second argument will be the position counter. And then go on to the next word, and the next word, and the next word, and you're done. Okay, that's your whole process file method. Is one loop. It's a while loop while has next is true. Call next to get a string, pass that through cleanupWord to get a cleaned up word. If it's not empty, increment the position counter, call add reference, go back to the top of the loop. When you're done, close the scanner, and you're finished. Alright, so we'll break down some of these methods into pseudocode in a few minutes. So here's a sample program for testing this, and all this code is available on the server, including a working indexer class. So if you want to make your own main programs and see what they do, you can play with that. So here's a PA2 test class that basically constructs an indexer and then tries some things that don't make sense. For example, trying to look at the value of the indexer before I've processed a file. Asking how many times the word test appears in my index when I haven't processed a file yet. So all these things I haven't processed a file. None of them should blow up. Okay, they should give you reasonable returns, mostly -1s. And now I'm going to try to process a file that doesn't exist, right? Unless you have a file called badfile.bad. So the file doesn't exist. My status should be false. So this should print out false. And then when I try to do things with that index, like, you know, tell me how many words were in there and so on, I should be getting my -1s. So this is the edge case where we haven't processed a file. This is the edge case where we tried to process a file but couldn't. And then here's the case where we successfully process a file. So I'm going to open up testfile.txt. You can pull that down from the server. And I'm going to print out the status. The status should be true. I'm going to print out the index by just concatenating it to a string, and that's going to give me a nice list of my whole index. I'm going to look for a word that's not in the input, right? I'm going to look for a word test that is in the input, and then I'm going to loop through and ask for the negative first, 0, first, second, third, fourth, fifth, and sixth locations of this word. And I'm going to ask for the number of unique words. All right, so here's my test file. Just you know, nonsense. And when I run my program, here's what I get, right? When I try to print the index, it's null because I haven't processed. All these methods return -1. When I process a file that doesn't exist, the status is false, the index is null, all these methods return -1. When I process my good file, the status is true. All right. When I say let's print out the index by just concatenating IND to a string, here's what IND got turned into. It's this really nice human-readable description of my index. And this is saying the word A occurred in position 3, no was in 17, or was in 16, yes was in positions 15 and 29, and so on. And if you go through this input and you break it up into words, this is a test. You can see the word test appears in position 4, right? Well, down here, when I look at test, it's telling me test occurred in positions 4, 20, 26, 27, 28. No instances of bad, 5 instances of test, and then when I call my location of, first location is 4, second location is 20 for test, and so on. When I ask for the 6th location or the negative first location, I get -1, and number of unique words is 19. All right, so put this in a PA2 subdirectory under your repository. Make sure it's called indexer, which means it's in a file named indexer.java, uppercase I. And if you have other classes that you're breaking this into and you have a make file to go with them and so on, go ahead and put all that in and upload it to your repo by the deadline. And you can read the grading rubric. It's pretty straightforward. So let me dig into some of this code and some of this pseudocode. And please ask questions as we go through this if they come up. I feel like information such as what the subdirectory should be named should be at the top of these documents. Okay, well, you could flip the document over. I usually put something at the bottom for submission or for grading that will do that. But yeah, I could see an argument for putting them in the beginning too. Well, making the directory repo is the first thing you do, which is good. This should be the first thing you do. But I know for a fact that's not always the case. All right, so let's go through some algorithms and pseudocode related to this. So first of all, let's talk about hashes. So we're going to be using something called a hash map. And the basic structure of a hash map, or a hash, is like this. We have keys and we have data associated with them. This is usually called value. And remember, from 222, we can think of this as just an array. But we don't treat it like an array. We treat it like something that can be indexed by key. So we can say, give me the value associated with key such and such. And if there's any entry in here where the key is such and such, we get that value back. Okay, so in this case, the keys are going to be strings. And these are going to be the words that we found in our file. And the value is going to be a linked list comprised of integers. And there's going to be locations of that word in our file. So this is your index. Okay, this is the list of words, and for each word associated with it is a linked list of locations where that word appears. So let's take a quick look at a hash map. So hash maps are generic also. They take two different types of arguments, one for the key, one for the value. We have to tell it what those are. The type of object for the key is going to be a string. The type of object for the value is going to be a linked list bracket integer, because linked lists are also generic. So we got generics inside generics. It's awesome. We construct a linked list just by saying, or a hash map just by saying hash map. We don't have to pass any arguments to it. And then once we have a hash map, we have all these methods available to us. And some of these take keys, some of them take values, some of them take both. Okay, so for example, suppose we want to know if an object is in our key, we can say, in our hash, we can say contains key. So if my hash map is called IND, or index, let's call it index. If my hash map is called index, I could say index dot contains key parentheses and put in any word. Well, remember, a word is a key is a word. So I could say index dot contains key parentheses quote hello. And that'll give me a Boolean telling me if hello is contained in our hash or not. If I want to add something to my hash, I can use the put method. I can say index.put parentheses and list the key, comma, and the value. If I want to retrieve something from the hash, I can use get. I can put in the key and it'll return an object of type whatever v was, which for us was a linked list. So what happens to this as we process our file? So suppose our input is this is a test. And I'm looking at a cleaned up version of it. It might have punctuation and upper lowercase, but as soon as you read a word from the file, you're going to run it through your cleanupWord, and you're going to end up with words like this. So what are we going to do? We start off with our hash map. It's completely empty. Okay, this is our object called index. So we get a word, this. We have a position counter, which is initialized to 0. We get a word, we clean it up, it's not empty. Okay, bump up position counter to 1. Check your index to see if you have a key which is equal to this. And you won't because it's empty. So add the value this to your key, to your hash, right? With a key value of this and a value of an empty linked list. Alright, so this will get stored somewhere, like this. And there'll be an empty linked list here, something that has no nodes. And now, go into your index, look for the linked list associated with this word, and add the position count to the end. So this pops a node over here with a value of 1. Okay, that's all you got to do for every word. Ingest the word, clean it up, search your hash map. If it doesn't find it, add this word to your hash map with an empty linked list associated with it. and then pull out the linked list associated with this word, add your position count to the end. And you just do that in a loop. Alright, so we ingest the word is, it's a good word, we bump up position count. We look for is in our index, it's not there, so we add it and it gets stored somewhere. And we store an empty linked list. And now we pull out the entry associated with is, which is this empty linked list, and we add a node to the end containing the position count. Pull in bump up position count, gets stored somewhere, empty linked list, add a node with a 3. Alright, now we pull in the next word is, it's a good word, bump up the position count. Look through your index, see if there's a value already stored associated with the key is. Well, there is. So the value associated with this is this linked list containing one node. Add a new node containing the position count to the end. So there's a 4. The linked list is a list of type integer, correct. Yeah, it'll be uppercase I integer. Alright, pull in the next word, this. It's a good word, bump the position count. Search through your index for the key this. You find it. Grab the linked list. Add a node to the end containing the position count. Grab bump up the position count. Look for a key. You find it. Grab the linked list. Add a node to the end with the position count. Ingest the next word, this. Bump up your position count. Look for the word test. You don't find it. Store it associated with an empty linked list. Now pull out the linked list associated with test, which is this empty list. Add a node to the end containing the position count. So after processing this input, this is what your index looks like. And it has all the information you need to answer any queries about the index. How many words are in there, where a word occurs, and so on and so forth. Alright, and this is really just calling some methods in the hash map class and in the linked list class. You don't have to do any real work. You do not have to write a hash function. You don't have to think about collisions. You don't have to think about sentinel nodes. You don't have to move down a linked list to get to the end. None of that stuff. Okay, that was 222 when we were creating these things ourselves. But now we're using them. They already exist for us. They're in these classes called hash map and linked list. So how do I tell if my word is contained in here? Contains, right? Call that method in the index. And if it doesn't, you know, call your put method. Put associated with the word, an empty linked list. How do I make an empty linked list? New linked list, angle bracket integer, paren paren. That's an empty linked list. And so you might find yourself writing things like this, index.put word, comma, new linked list, angle bracket integer, paren paren paren, semicolon. Thinking of objects, right? Index is a hash map object. It has a put method. What does the put method want? It wants two arguments. It wants a key and a value. Key is a string, value is a linked list of integers. So first argument is a word, assuming that word is what you're calling, you know, what you ingest. And the second argument, I need a linked list of integers that has no nodes. Well, just construct one. I don't need to save that in a temporary variable because it's stored inside my hash map. It's associated with this word. Now if I want to add position count as a new node at the end of the linked list associated with word, what do? I can say index.get word. Alright, that's a linked list. How do I know? If I look at the get method, it takes in a key of type object. Well, it takes in a key. For us, it's a string, but it returns an object of type v. V was a linked list of integers. So the get method this returns a linked list. Well, how do I add a new node to the end of a linked list whose value is position count? Well, take a look at the linked list class again, and the first method you find is add. Append the specified element to the end of the list. So I can just say index.get parentheses word dot add parentheses position count. That one statement does all this work for you. It goes through your hash, it finds the entry associated with a word, it pulls that out, it treats it as a linked list. It starts with the first node, it moves down until it gets to the end. It creates a new node, it sets the new node's data value to position count. It gloms that onto the end, sets its pointer to null, sets the last node to point to it. You get all of that just for this one line. Okay, that's where you want to be heading, where you can sort of think about things like this and you know, get to this instead of doing all that stuff that I just mentioned yourself. Right? Because when we can write something like this to do all of that stuff, we can start, you know, imagine what our complex statements can do. Right? Imagine what you can do with a 5,000 line program if, you know, a few characters like this does all of that. Okay, this is the real cell of object-oriented methodology. All right, let's look at one more. Let's look at this cleanupWord. So you have some string that's coming into this method. I'm going to call it in, right? The suggestion in the assignment is basically build an output string. So start off with a string output, which is just empty, and go through each character of your input, and if it's a letter, convert it to uppercase and append it to your output. And when you're done, your output should be your cleaned up word. So how do we iterate? Well, for loops work well. So I equals 0, our usual way to iterate on a string, I less than in.length. Length is a method. All right, how do we know if the ith character of our word is a letter? Well, our string class has something called char@, which we can pass an integer, and it'll give us the nth character if we pass it n. And so we can say in.character@ I. That's the ith character, and we want to know if it's a letter. Well, the ith character is a char, and character is a class, and one of the methods in the character class is called isLetter. So isLetter takes a character and gives you back a Boolean. Well, here's a character. So if we say .isLetter, right? Again, we're glomming together methods from objects, right? That's a string. That's a method that gives us the ith character. This is a character. Characters have an isLetter. isLetter takes an argument. Doesn't take an argument, but it returns a Boolean. So this whole thing is a Boolean telling us if the ith character of in is a letter or not. So if it is a letter, then append character I. And let's take that character and convert it to uppercase, because characters also come equipped with a toUppercase method. So toUppercase will convert the character to upper. So take in character at I, convert it to uppercase, append that to out. And when you're done, just return out. All right, that's some of what this may feel like. In Java, can you treat the string like an array and change the string in line without using a second string? I don't think you can change the ith character. That would be a nice thing to be able to do. You can replace. That's just systematic, regular expression. You could do it with a regex. That would be pretty extreme. I don't think there's a method in the string class to do that, but there are a lot of ways you could do it pretty painlessly. For example, you could take the substring up to but not including the character you want to replace, concatenate the character you want to replace the next one with, and then concatenate a substring from the next point to the end of the string. And that would still be a one-liner. That's if you know the character by position. All right. I posted some. Yeah, it does create a string anyway. I posted some sample code in the public area under file IO that talks about, we did scanners on Wednesday. It talks about how do you do scanners to read from a file. But it's going to take a little bit to go through that because we have to start talking about exceptions when we do that. So my suggestion is to get started on this before Monday, just read from standard in, system.in. And if you want to use a test file, just redirect with a less than sign. So you can say Java, your program less than test file. And that lets you, repeatedly and consistently feed a file that you can ingest. And on Monday, we'll go through details of how to actually open a file from inside Java. But it takes us into a few other topics, and I want to finish talking about this instead. But that lets you get on the air quickly. Let's see. All right, well, let's talk about ways that you can approach this. Okay, and again, if you've already got your own idea how to do this, that's fine. Go ahead and run with that. But if you're looking at this and you're kind of like, I have no idea where to even begin, right? Here's some ideas on where you might begin to make progress on this. So first thing would be just make a skeleton indexer class. Okay, class indexer curly curly. All right, and add a process file method. Okay, so what does process file do? Well, it's going to read words from a file. In this case, it's going to read words from system.in, and print them out. Okay, it's a starting point, and it lets you play with the scanner class, using it to ingest words instead of entire lines. Sorry?
Yeah, like right now it's breaking up bad.
Oh, is it?
Yeah.
Okay. Yeah, my machine's been generally misbehaving today. Let me turn off this camera. But I don't know what else I can do. Let me stop my share and restart it. I don't know if that's going to be any better or not. But presumably the recording will be clear, so worst case, go back and catch the recording. But we're out of here in 3 minutes. All right, so here's an example of using a scanner with has next and next instead of has next line and next line. So has next basically ingests everything up to a white space. So you can basically use this pair to pull in words. And then in this case, instead of using system in, I use this new file thing. But like I say, don't worry about that. You can go ahead and just read from system.in until we talk about this on Monday. Let's see. Let me kill my other camera. That will probably help some. All right, so let's go through recommendations. So start off with a simplified process file. It just reads an input and prints it out one word at a time. Okay. Don't worry about cleaning up the word. You can make your test file all uppercase, no punctuation, just separated by spaces. All right. And then go ahead and start making a hash map. So this lets you work with the hash map class. Make yourself a hash map to store the words in. Don't worry about linked lists yet. Just make it a hash map of, words and integers or something. And just store zeros for the integers. But start putting your words into the hash map. Okay? So that that you can work with that class and start storing things in there and start looking to see if things are in there. And once you do that, you can print out the value of your hash map by appending it to a string. And so remember, at the end, you want to be able to do something like, say, after processing good file, index equals, and just concatenate the name of your index. Well, when you try to concatenate a hash map to a string, it calls the hash maps to string method. And guess what? This is what it gives you. It gives you a string that looks like this. And it's this nice list of key value pairs. In this case, the value is a linked list. So this is linked lists to string method being used to generate a string of values separated by commas. And the words are strings. So this is another, method. Your toString method is really just going to return index.toString. Doesn't have to do anything more than that. Doesn't have to traverse list. Doesn't have to search through the hash. It's really just using the toString method in the hash map. So you can play with that once you start getting a hash map. And if you do that, it should show you all the words that you added from your test file. And now you can go ahead and you can try to add a linked list to be associated with each key without storing values in the linked list. And then go ahead and add a word counter that increments each time you ingest a word, and add that to the end of your linked list. Each of these is really an incremental step beyond the previous. It's calling one or two methods somewhere, but it's helping you figure out what methods to call and how to call them. And yeah, the countdown timer is in Java. All right, so we are out of time according to the Java countdown timer. So that should get you going on PA2. And sorry about the audio quality. Again, this will be posted, so you should be able to review it up there. All right, have a good afternoon, have a good weekend, and I will see you Monday. Thank you.